Speaker is Geoff Whittle from Victoria University of Wellington, and he has the intriguing title, Is There Hope? Thanks, Geoff.
Thank you, Dylan. My first hope is that, start off with, there has to be hope. There has to be hope that the technology works to start off with. Is this microphone's working? Oh, and look, that thing. And now, third hope is that the clicky thing works. Awesome, okay. All right, so I'm going to begin by talking about a class of matroids called K-regular matroids. And I'll just try to give you an idea of what this class is and to start off with. So I've got some algebraic blah here, which I'll describe, and it's perfectly fine. You extend the rationals by K independent transcendentals, and now you've got a field, and I'm considering matroids representations of matroids over that field. Now, as was said in the previous talk, you can think of a representation of a matroid over a field as a row space. Take a subspace, it corresponds to a row space of that matrix, but in my part of matroid theory, you just need a basis for that row space. In other words, you need a bounded number of rows. So I'll be talking about representations in that more limited sense. And I'll say that a matroid is K-regular if I can find a representation over all of that field in which all of the subdeterminants of my matrix have this property that they're integer powers of differences of distinct members of 0, 1, alpha 1, alpha 2, up to alpha k. Now, what does that actually mean? What it means is, if I can find such a representation, so subdeterminants is just take any square submatrix and you're allowed to permute the rows and columns to take whichever square submatrix you like. Then whenever you find the determinant of that submatrix, it's got to be something like alpha 1 minus alpha 3 to the 3, some product of things like that. And it's an elementary exercise, you go through it. And what it gives you is a certificate. If you've got a representation that looks like that, then you have a certificate that that matroid is representable over any field of at least size at least k plus 2, which probably takes me to my next slide. Okay, so this K-regular, and one could say I'm talking about the K-regular partial field here, and for those of you who know about partial fields, that's fine, and often there'll be partial fields in the background of this talk, but for those of you who don't know about partial fields, it doesn't really matter, but I'm going to sort of avoid partial field jargon, at least for the most part. So such a representation is a guarantee that I've got a class of matroids. So that class of matroids, and the reason for that is you just take your alpha 1 to alpha k and just choose k distinct elements that aren't 0 or 1 in the field that you care about and just call those alpha 1 to alpha k, and that's guaranteed to be a representation. So it just works and it's an easy thing. Now, why do we care about such the K-regular matroids? Well, there are some interesting special cases. 0 regular, so I don't have any of the alphas. That's exactly the class of regular matroids. And that's the class of matroids representable over all fields, and it's possibly one of the most well-studied classes of matroids of all time. So that's clearly an interesting class. From the point of view of this talk, it's interesting that it gives you precisely the class, it's exactly the class of matroids representable over all fields. And this sort of generalises a bit. 1 regular, which are more commonly known as near-regular matroids, that turns out to be precisely the class of matroids representable over all fields of size at least 3. We know it's contained in that class. If you're near-regular, you're representable over any field of size at least 3. But it turns out to be exactly that class. It turns out to be exactly that class. And that's a very old, sadly how old I'm getting. I'm not going to tell you how old that result is because it would give you an idea of how old I am. So that's a long known result. And at the time I was sort of excited by this idea and I thought, well, surely this will generalise and are we onto something here? And the answer is I shouldn't have clicked that then. I'm clicking the wrong button. Go away. So are we onto something here? And the answer is no. If we look at the class of 2 regular matroids, that's guaranteed to be a class of matroids representable over all fields of size at least 4. But it turns out that it is not the class of matroids representable over all fields of size at least 4. The class of matroids representable over all fields of size at least 4 is a bigger class. And so then you could actually say, and same with 3 regular, that is a subclass of the class of matroids representable over all fields of size at least 5. And you could say, well, so much for these K regular matroids. They're not very interesting, are they? Because they don't correspond to any interesting natural class of matroids. And yet we still went to the trouble of finding the excluded minors for 2 regular and 3 regular matroids. And when I say we went to the trouble of finding the excluded minors so not for K regular matroids in general, I'll just quickly say we know the excluded minors for regular matroids, we know the excluded minors for near regular matroids, so I'll talk about who we means in a moment. And we went to the trouble of finding the excluded minors for 2 regular matroids and 3 regular matroids. But it doesn't seem like a very well-motivated problem, does it? Because it doesn't correspond to some natural class that you might care about coming from the world of matroids. But there you go. I just seem to be going the wrong way with this thing all the time. I'm not allowed to move my thumb from this particular spot. First of all, there's a bit of a lie. We didn't quite get the excluded minors for 3 regular matroids. It's not a Trumpian lie, like it's not a completely outrageous lie. We believe we know what the excluded minors are, and we've shown that I think there's at most 17 elements in an excluded minor, and and reduces it to a computer check to doing it up to a certain size. And if you really, really, really cared about it, I'm sure that, that you could actually do some more analysis and do that computer check. But for the sake of argument, let's say we know that class. Now, there was a lot of work getting that result. I think at least all of these people here, James Oxley, Charles, Semple, Nick, Brett, Ben Clark, Dylan, Carolyn, Deb, Stefan Bunzram, Rudy Pendarvin, all were authors of papers that played necessary steps towards getting this, this result. So there are 17 excluded minors for 2 regular, and modulo the computer check eliminating some other possibilities, there are 33 excluded minors for 3 regular. And the question is, who cares, right? Why would you care? And I really mean that because the work was incredibly painful, right? It was a lot of unpleasant case analysis. None of the, if there's a book, none of these proofs are in the book for good reason. It's technical. But I'm going to give you an idea. So the techniques for this result are something that I sort of think of as calling it the standard technique for proving an excluded minor result in this world. And it works for some classes. It's a technique that will give you the excluded minors for GF3, GF4. And in fact, you can think of this technique as really evolving from the techniques used in the excluded minors for proving Rota's conjecture for GF4 that Jim and Bert and AJ did quite a few years ago now. It works for the class of regular matroids. In fact, the techniques for GF4 actually came out of an evolution of the techniques of Bert Gerard's for regular matroids. Near regular is the class we talked about before, and these are 2 regular and 3 regular. So what is the standard technique? Well, the standard technique is you first of all need to know that your excluded minor has a certain type of matroid. So this is very, very broad brush, but I'm going to talk about it a bit so you know we need to do this brush work. We can assume that the excluded minor has a certain matroid which we will call a stabilizer. It's a matroid. And we're interested in excluded minors that have this particular matroid as a minor. And we say, well, let's assume our excluded minor is very big, but it is an excluded minor. Now, what a stabilizer means is that within your class, and I'm telling white lies here, within your class, if you're 3 connected or something close to 3 connected and you've got the stabilizer as a minor, you know that a representation of that stabilizer extends uniquely to a representation of the bigger matroid. Now, uniquely is a great word because it means many things, right? Uniquely what up to scalars and things like that. So uniquely up to actually scaling in this case. And so then what we do is, well, it's an excluded minor, so it's not representable over the field or partial field that we're interested in. So what I'll do is, the minor is quite a bit smaller than this big thing that's, because we can assume the excluded minor is big, because if it was small we'd be happy, so we've got this thing that's big, that's purported big excluded minor. We find 2 elements that we can remove and delete and keep the stabilizer and the connectivity property. Our stabilizer then extends to a unique representation of this thing over our algebraic structure, and we can put in X and it extends. We can put in X and that gives us a representation, and then we can forget about X and put in Y and that gives them the representation, and we can stare at the matrix we've got left. Something must go wrong because our matrix is not representable over this thing, and our matrix must have some determinant that's either 0 when it should be non-zero or non-zero when it should be 0, and we call such a determinant a bad subdeterminant. Right? We call such a determinant okay, we're away. We call such a determinant a bad subdeterminant. And there it is, and it's a big thing. Well, actually we can pivot, and pivot just means our matrix has, we can think of the rows as corresponding to the basis and the columns as corresponding to a co-basis or the complement of a basis, and we can actually pivot and still have the same structure, so switch things in and out of the basis, and if we do that, we can bring our bad subdeterminant down to size 2 by 2. What happens then is, in the process of doing that, that previous picture had that picture of N, our stabilizer in the top left-hand corner. That was a nice picture. That was represented as stabilizer as a visible minor. We can actually... Oh, Dylan, can you tell me, when does my talk have to stop? Yeah. Okay, visible minor. Visible minor is that you can see it. The elements that you can delete to get the minor are the columns, and the elements that you can contract to get the minor are rows, and then the minor becomes visible. But in the process of making my bad subdeterminant, my minor is no longer visible, and you can see from the picture, it's invisible, right? That's clear. So that's our bad subdeterminant. So what happens then? Well, the nice thing about when I pivoted and had that 2 by 2 bad determinant is I can remove any column I like, apart from the X and Y column, and still see a bad subdeterminant. But there must be a reason, but that matroid is representable, it's still got a bad subdeterminant. So we've lost some information that we needed, and I said that badly, but I haven't got time to be explicit. But we've got the actual picture I gave you a certificate for non-representability. If I delete a column or contract a row, I lose that certificate, yet I'm not losing that bad subdeterminant. So how could I be losing the certificate? And there are 2 ways that we can lose that certificate. One way is that we can lose the connectivity property. And if we lose the connectivity property, and the connectivity property is something like 3 connected, that turns out to be not particularly a difficult problem to resolve. So I'm just saying that, I haven't got time to say why. The other thing is that we lose the stabiliser. So it turns out that we've got a situation where we've got the stabiliser as a minor, and essentially all the columns, if I remove any one of them, I lose that minor, and all the rows, if I remove any one of them, I lose that minor. And that corresponds, that's the problematic situation. And that corresponds to a situation we call fragility, where I have a matroid with a minor that has the property that for any element, if I remove it in the wrong way, I'll lose that minor. For every element, I'll move it in the wrong way, I'll lose that minor. If this was like these conferences used to be, then I would actually start to say this is just like having a deletable vertex in graph minors. But I feel the audience has changed, and I don't feel like that's quite the thing to say. But anyhow, so the real problem is that when I remove a column or a row, I've lost that small minor. And therefore, I don't have this certificate for non-representability anymore. And what we would like to say is that if I'm sufficiently large, I would have an element that I could delete or contract and keep both the connectivity and the minor, and that's, so the problem is fragility. And that means to use the standard method, we need to, we've got a certain class of matroids and a matroid N, and we need to understand the structure of the N fragile matroids in that class. That's the structural problem we have to solve. And if we go back to GF4 representability, then it turns out that the GF4 representable U24 fragile matroids are a class of matroids called worlds. Now, Jim, you know, like, sometimes the universe is kind, I have to say. And this was one of those times when Jim and Bert were working, and AJ were working on this problem many years ago, because worlds are a very easily understood class of matroids. And what actually happened in the you can have very large worlds that will be fragile, but if you put them in the matrix in the right way, where the turns out you can do a couple of pivots and get yourself away. So that was just, unfortunately, the universe is not always nice. For the problem that we were looking at, for 2 regular and 3 regular, we needed to understand the structure of 2 regular U25 fragile matroids. And that means our thing is U25, and I'm forgetting about 3 regular just for simplicity. And that was a structural problem we needed to solve. You can solve it. The answer's more complicated than worlds, but it gives you a class of matroids of bounded paths width, and you can sort of draw pictures of them and things like that and finally understand what they are. And you can do enough with enough work, you can eventually get there. And it was a lot of work. And work I didn't really, to the extent I made a contribution to it, I can't say I really enjoyed the work much either. It's just one of those, why did I do it? Why did I? Well, so okay, why would we care? So I've got a sort of a slight confession. There's part of me that sees myself as an applied mathematician. And actually, it's not really quite true. I mean, I believe in mathematics, some problems are just innately compelling, right? And what are, Peter, I'm putting you here. What are examples of 2 problems that I think are just innately compelling? One problem is the twin prime conjecture. If anyone's got a good idea for that, tell me how it goes. But another problem is Nelson's conjecture, which is just a conjecture of Peter's, which I think is an incredibly beautiful conjecture, which just says that the property of there existing a field over which a matroid is representable asymptotically is just a statistical problem about the number of bases and non-bases. That is so radically different to what I originally would have thought that the answer would have been. And yet so obviously true once you think about it, that I think that's an innately compelling conjecture. So some conjectures, or similar sort of, so we all know that some conjectures are innately compelling. So I'd say that, and then other problems are interesting because they just might have applications towards a genuinely compelling problem. So the real reason we looked for the excluded minors for 2 and 3 regular matroids is because we felt they just might have applications towards 2 genuinely compelling problems that I think are genuinely compelling. Of course, the good thing about this is the term genuinely compelling is an undefined term, right? So it can be whatever you like it to mean, and that's fine by me. So the first genuinely compelling problem that we might expect is the excluded minus for GF5. And so the thing about, oh, by the way, this thing about the technique I'm talking about, it's just not going to work for most classes of representable matroids. You can just show it's a technique that only goes so far. But it actually does work for GF5. If we had the computational power, we could make it go for GF5. So we can use this standard technique to find the excluded minus for GF5 using the Penn-Dove and Van Zwaam hierarchy. And I'm not going to say, I'm going to skip over exactly what this hierarchy is because I haven't got time. But there are 5 layers. The top layer is all GF5 representable matroids. Layer 5, the very bottom layer is the class of 3 regular matroids. And that was a surprise to me because they originally described as a hierarchy of partial fields, and the bottom layer had a description as a certain partial field, but that matroids representable over that partial field turned out to be matroids that are 3 regular, as Nick explained to me. And the good news about that is Nick explained to me how to do it, and then it's in our paper, and some things I thought it's in a paper with my name on it, even though I had no... Nick was the person that completely worked it out. So what that means is that when we've got having the excluded minus for 3 regular matroids, we can think that as a first step towards getting the excluded minus for this compelling problem, which is getting the matroids representable over GF5. And so that means we know the excluded minus for layer 5 modulo computation. And now you look at these excluded minors, and some of these belong to layer 4. So some of them are excluded minors for GF5, and hooray, you found some. Some of them are excluded minors for layer 4. And they're the things you've got to use as stabilizers to get the excluded minors for the next layer up. So you rinse and repeat up. But each time you get a more difficult fragility problem. And already you're actually at the very limits of our computational ability with current techniques. So I think, and so in a sense, theoretically, you've got a way of going through these layers and getting the excluded minds for GF5, but each of these has a fragility problem to solve, and I think using the standard technique, it's just plain hopeless. Yuck. So is there hope? Okay, is there hope for the excluded minds for GF5? And the answer is not using the standard technique. So not using the technique. You're just going to end up with fragility problems that you can't solve. But you could change the game and find another technique. There's another thing that you can look at called bad subdeterminant fragility. Can't say anything about that. But my current belief is that the horrors of fragility are intrinsic and will show up in the search for excluded minors. Now, and that's actually, when I say that's a belief, it's a belief, not a conviction. If you have to ask me which direction I put money on, that's which direction I... What makes me not really convinced about putting money on my belief is that Jim Geelan is more hopeful. And I don't know, Rutger, are you more hopeful? I'm not sure. But Jim and the problem is that Jim's smarter than me, So when you make a bet and you know that someone is certifiably smarter than you, and they bet in the other direction, is this good? It's not necessarily good, but anyhow, you still have to go with you. So my feeling is that I think there is no hope for us ever getting the excluded minors for GF5. Certainly not within my lifetime, but I also believe not within any of your lifetime. I'd love to be proved wrong, of course. Actually, a realistic, just very quickly, there's another class of matroids called dyadic matroids. I'm not going to talk about them, but that's a class that we should know the excluded minds for. We don't. And I think that's a fascinating problem, getting that, but I haven't got time to say much about that. Okay, the other problem I think is compelling is understanding the matroids representable over all fields of all sizes, at least 4. I mean, we actually know a lot about the matroids representable over GF3 and other fields, and I'd love to be able to say we know a lot about the matroids representable over GF4 and other fields. Well, say we call this class M4. I had a fantasy, that... First of all, my fantasy went like this, find the excluded minors for 2 regular. And now some of these belong to M4, and there they are, they're beautiful names, P8 minus, TQ8, U36, F7 minus minus. And I know this because I looked them up when I was preparing this talk. But anyhow, and my fantasy was that you actually So I thought, oh, well, the Matroids represented by raw fields containing Geoff. They're probably not much bigger than 2 regular. You've probably just got these thin classes sitting out of 2 regular. But that turns out, so the idea is what you do is you look at each of those Matroids, understand the members of M4 that contain them, and then you've got an understanding of M4. And maybe they lead to thin classes. Now, there's 2 issues with that. First of all, they don't always. The class containing F7 double minus is thick, and my definition of thick means contains members of unbounded branch width, and that's the case for that class. Doesn't mean it's difficult, it's just thick. And the other thing is that thin classes can be an absolute pain in the neck. And just because, so thin classes of small branch width or parts width, they can still be horrible things to sort of get your hands on. So that's just, so, the question is that we did, so the actual, just times very quickly, so I'm just babbling. I'm starting to sound like Joe Biden now. That's a real concern. Okay. Is there hope for Matroids to represent all over GF4 and other fields? I think it's going to be a much more challenging journey than we anticipated. I had this fantasy that getting excluded minus for 2 regular would take you somewhere from which it would be a reasonably easy thing to do. But the thing is that there is other hope, and the other hope is coming from we actually had knowing those excluded minus gives them insight into knowing certain partial fields that are definitely interesting. And if we knew something about what the minor minimal things that were not in those partial fields, and I haven't used partial field language in this talk, but more or less everything is about partial fields in this world. But partial fields are not to everyone's taste, and Dominic Welsh, who many of you will have known, died not that long ago. He is sadly missed. He was a larger-than-life personality and an amazing person. And his way, that sort of algebra was not to his taste. And if Dominic were to give his idea of what a completely incomprehensible maths talk would do, he would say, oh, well, the first talk would be, the first sentence of the talk would go, oh, let P be a partial field. You know, that was his sort of idea of beginning a talk with an incomprehensible thing. So that's just a little bit of a memorial to Dominic. He was not afraid of criticising partial fields. And that's a bit of a segue to Nick's talk, because Nick's going to talk about a possible partial field approach to this question. I think this question does have hope, but it's going to be a long and difficult journey. Okay, thank you very much.
Is there a question for Geoff?
Jim. Yeah, I know. No. Well, not. It's got to be thin, right? You've just got to. But so Nick and James and Charles and I spent a week or 2, perhaps a year or so ago, just working on trying to understand, looking at these, and there didn't seem to be anything simple about Year 3-6. But having said that, we spent some time on it, and then we got depressed. You need someone who's young, got a 3-year postdoc, and say, like, I don't know. Initially I would have thought it was straightforward, but yeah. I mean, you can put triangles, make things into triangles, and you glue things onto triangles, and then weird things crop up. Yeah.
Okay, let's thank Geoff again.